One immediate application of calculus is in probability, in particular continuous probability density functions, which we'll define in a second. But before I do that, I just wanted to ask a couple questions above to get to sort of prime your intuitions about what we're actually doing when we find probabilities of continuous functions. So if you imagine throwing a dart at this number line, and you kind of imagine that really there's only a horizontal dimension to this, so you're not going to hit below or above, you're going to hit somewhere on this number line, exactly. And you're going to hit in between 0 and 1 somewhere. If you ask what the probability of hitting 0.25 is, so 0.25, if you imagine that number being right about here, what's the probability you're going to hit that exactly? So this could cause a debate or a discussion in a classroom ranging from anywhere between 10 minutes to an hour, depending on the sophistication of the class and their mathematical background, etc. But briefly, or in a nutshell, we really want to think of this as being or having probability of 0. And the reason is because there are infinite number of numbers in between 0 and 1. And so, I mean, if we, this is probably not the best, mathematically correct way to think about this, but 0.25 is one number out of the infinite we see, and so that would be 0. Now this isn't technically right because you can have an infinite number of numbers being in a being a total amount of possible outcomes, and the probabilities don't have to be 0. But just one thing to just point out is that the real numbers on the number line are so dense that there's no way you could possibly hit 0.25 exactly. It's just it's an impossibility. And same goes for any other number. What you can ask though is the probability of throwing the dart and hitting a region between two numbers. So between 0.25 and 0.5, for instance. So what would the probability be of you hitting this? Somewhere in this region. Well, now we can clearly make an argument that that is 1/4 of that entire distance. So we should expect that we have a 1 out of 4 chance of hitting in that region if we throw it randomly. All right, so notice the difference. Once we're talking about a region or an interval, we can actually make sense of problems in which the sample space is what we call it, is continuous. So this leads to what's called a continuous probability density function, which is defined below. So it's a function, so that's the key idea. It's a function. The domain are all real numbers, and what has to happen is that your function has to be always positive or equal to 0, and when you integrate from negative infinity to infinity, you get 1. And that's because we want probabilities to add up to 1. Now, in practice, you don't always need the negative infinity and the infinity. Certain situations you don't need to be going in infinite directions on both sides. However, this is just in general. Even if you went out to infinity and negative infinity and integrated, you have to end up getting 1 as a final sum. And then the probability associated with an interval is just the integral from a to b under that function. So an example usually makes this really clear. And when you take a probability or statistics course, you'll end up just getting a lot of probability density functions, and then you'll be asked questions, probability questions, and then your answers to those will often just be using the integral to answer it. So we'll look at one example. So here we're told that experience has shown that the lifetime of certain brand of light bulb follows an exponential probability model given below. So the function, so notice it's piecewise. It's 1 over 3,000 e to the negative t over 3,000, as long as t is bigger than or equal to 0, and then it's 0 everywhere else. So one thing I just want to note, if you do this on your calculator, the integral from 0 to, now we don't have an infinity button, but if you just put in a really big number, you'll get something. I mean, you'll get 1, all right, and that's important. Now I could have put a negative infinity down there with the 0, but this function's 0 from negative infinity to 0 anyway, so there's no real need to do that. So it's a probability density function. And we're asked, or we're told that a money-back guarantee is offered on bulbs that fail to last at least 3,300 hours. So a money-back guarantee is offered on bulbs that fail to last at least 300 hours. What's the probability that the company will need to refund your money on the bulb you just bought? Well, they'll refund if the bulb fails to last at least 300 hours. So another way of saying that is we want to find the probability that the time at which the light bulb burns out is less than 300. And that's what this notation says. So that means that we want to take our integral or we want to take our probability density function, we're going to put it in our integral, and we're integrating from 0 all the way up to 300. So if you look at our picture over here, what it's telling us is that this blue area, which I'm making red apparently, this blue area is going to give us that probability, right? So if you wanted the probability that the bulb will last more than 300 hours, then you would need to do, so I'm going to just put that here. So let's say it lasted more than 300 hours. You would use the same function inside. You'd integrate from 300 to infinity. Now we don't have an infinity button on your calculator, so you just put in a big number like 1,000 or something like that, and that should give you a close enough approximation. But that's what a probability density function will give for us. I mean, I could ask any range of questions. I could say, what's the probability your light bulb will last between 200 and 250? In which case you'd put 200 and 250 in the lower and upper limits of integration, respectively. So that's just the basic introduction to probability density functions. I'm not going to do much more with this other than compute the answer. This ends up being about 0.095. So there's a 0.095 chance that you're going to get a refund, or that the bulb will last less than or fewer than 300 hours. It's worth noting the shape of this function. It sort of makes sense that it has its shape, right? I mean, there's a relatively as time goes on, there's probably a lesser and lesser chance of you actually having a light bulb that lasts as long as past 300, 400, 500, 1,000 hours. So we should expect that this probability shape would decrease as time goes on. So in any case, probability density functions are generally pretty easy to apply. What's hard is to derive them, which is not something you'd ever be expected to do unless you take a higher level math course. But there's an introduction to probability density functions.